Hi all. For this lab, we're going to be playing with random walk, sometimes called Drunkard's walk, algorithms. Specifically, we're going to be exploring a self-avoiding random walk. First, we'll go through the lab problem description. We'll then walk through a couple of example simulations of the Drunkard's walk to make sure we understand the process described. We'll then move on to an example in which we use a Monte Carlo process to estimate the probability related to the Drunkard's walk, which is the main goal of the lab. So let's get started. Here is the problem description. A drunkard is trying to make his way home after having wasted several hours of his mortal life in a tavern. He finds himself in the dark at the center of a field, which we can model as an n by n grid, where n is an odd number so that the drunkard can be placed at the exact center. The drunkard then repeatedly stumbles one cell in a random direction, north, south, east, or west, such that each direction is equally likely, but under the constraint that he cannot stumble to a cell he has already visited. If he stumbles off the field, we say that he has successfully escaped and made his way home. If he stumbles to a cell such that he can no longer stumble to a cell that he hasn't already visited, however, we say that he has blocked himself in. In this lab, we're interested in finding the probability that he will escape a field of given dimensions. Notice that this is a difficult probability to calculate directly, since we would have to consider many paths the drunkard could take while stumbling around even a relatively small field. This is why, in this lab, we're going to use computer simulations to address the problem. But first, let's make sure we understand the problem. Let's walk through an example simulation in which the drunkard successfully escapes the field. So here we have our drunkard in the middle of a 25 by 25 field, late at night, contemplating the poor life decisions that led him to this predicament. He's now going to stumble in a random direction. Since he hasn't visited any cells yet, that direction could be north, east, south, or west, with each direction being equally likely. And it turns out that his first stumble was due east. Now, since he has already visited the cell to his west, he can only stumble north, east, or south. Again, the choice will be random, with all legal directions equally likely. And it turns out that his next stumble was due south. Now he can only stumble east, south, or west. How about we sit back and watch him as he continues his shenanigans? And he has successfully stumbled off the field and managed to make his way home. Now let's take a look at a simulation in which the drunkard blocks himself in. Here he is again, in the same predicament as before. You'd think he'd have learned his lesson by now, but some folks just can't help themselves. Let's watch what happens this time. This time, he's walked into a cell such that the cells to his north, east, south, and west have all already been visited. He's blocked himself in and can no longer move. I'm afraid he's going to have to sober up where he is until dawn finally comes. Alright, now let's think about how we can get the computer to simulate this random walk. Basically, we're going to set up a loop that continues until the drunkard has either successfully escaped or has blocked himself in. Inside that loop, we choose a random direction that the drunkard can stumble in without stumbling to a cell he has already visited, and then move the drunkard in that direction. Finally, we return true if the drunkard has escaped, or false if he has blocked himself in. Pause the video now and complete task 1, which is to physically perform the simulation using a 4-sided die and paper to test your understanding of the problem, and part A of task 2, which is to implement the simulation in a programming language of your choice. For part A of task 2, it might help to output the path taken so you can check whether your code is working correctly. Also, be careful when identifying legal moves when the drunkard is at the edge of the field. When you're ready, hit play again to continue. Alright, now we're ready to move on to the main problem. That is, to use the simulations to estimate the probability that the drunkard will escape a field of given dimensions. As before, let's make sure we understand the problem by walking through an example. In this example, we're going to perform 200 simulations and use the relative frequency of successful escapes to estimate the probability the drunkard will escape a field of given dimensions. Of course, in your own work, you'll use a much larger number of simulations so that you can be more confident in your results, but we'll just use this number for now for illustration purposes. This time, we're going to let a random walk complete, in which case it has either been a success or a failure. Our first simulation resulted in a success, as shown in this slide. So far, the relative frequency of success, which is our current probability estimate, is 100%. Of course, with only one simulation, we don't have any confidence at all in this estimate, so let's run another simulation. Our second simulation resulted in a failure. So far, we have thus had 2 trials, with one of the trials being a success. So our estimated probability of success is updated to 50%. Of course, we still don't have any confidence in this value as a probability estimate, but we have at least seen that failure is possible. Let's run another simulation. The third simulation was a success. So we now have 2 successes in 3 trials for an estimated 66.7% probability of success, and so on. Let's sit back and watch as the simulations continue. Keep an eye on the probability estimate as the number of simulations increases. We're now on the 50th simulation. Notice that as the simulations accumulate, the estimated probability of success starts to stabilize. One interpretation of probability is the limit the relative frequency of success approaches as the number of trials grows without bounds or tends to infinity. And that's the idea Monte Carlo simulations are based on. Let's continue. We're now on the 100th simulation. As the number of simulations increases, we notice that the probability estimate continues to stabilize. After 100 trials, we have a probability estimate of 47%. Let's speed things up a bit for the remaining 100 trials. Finally, after 200 simulations, we have an estimated probability of escape from a 25 by 25 field of 46%. As already mentioned, 200 is a rather small number of simulations. This plot shows how the relative frequency of successes changed during the simulations we just saw. As we noted before, the probability estimates are quite volatile initially and then stabilize as the number of simulations increases. Even so, there is still notable volatility after 200 simulations, and I'm not sure how much confidence we can have in the estimated probability of 46% we obtained. In the lab, one of the goals is to get probability estimates to within 1% of the actual probability, so you'll need to adjust the number of simulations performed accordingly. Okay, so now let's think about how we can implement this. The basic idea is quite simple. We keep track of the number of successes encountered as we perform a large number of simulated walks, and then finally return the proportion of successes as an estimate of the probability of success. Of course, we cannot perform the infinite simulations needed to get the actual probability. Instead, we perform enough simulations to narrow our estimate down to within a chosen error level. As already mentioned, for this lab, that error level is 1%. Great. So now you're ready to move on to part B of task 2, which is to implement the Monte Carlo simulations and estimate the probability of a drunkard's escape from a field of given dimensions. After that, you can go on with task 3, which is to use the implementations to explore how the probability of escape changes with the dimensions of the field, and task 4, which is to create a video presentation of your implementations and results. And that's the lab overview. I hope you enjoyed the video. Have fun with the lab.